the topic of the day will be the further generalized numerical radius inequalities for Hilbert space operators. As you have already seen, this is a joint work with Professor Fuad Kitanik. So this is the work plan. We will say the abstract, what will be the topic and the results, then the terminology, auxiliary results, main results, and then the conclusion. So the abstract, we will introduce a new generalized numerical radius, this quantity, which is defined based on the generalized real and imaginary parts of an operator, as defined by Kitanik and myself in a recent submitted paper. We will demonstrate that this new quantity is a norm on the C-star algebra of bounded linear operators, and that it is equivalent to the standard operator norm. A key strength of this new concept is its generality. It encompasses and refines existing definitions and inequalities, including those previously established by, say, Husseini et al. And Kitanek in their papers. Furthermore, we will explore various new inequalities, including those involving powers of operators and operator matrices, providing extensions and refinements to previous results in the field. That the adaptability of this quantity through the functions h and g suggests promising applications and significant contributions to the ongoing refinement and extension of operator inequalities in functional analysis. Results in this presentation are based on the recent paper submitted by Professor Kitanek and myself. So the terminology is the usual as in the previous talks. Let H denote the complex Hilbert space with an inner product. Specifically, the numerical range is given by this, as usual, while the numerical radius is just the supremum of the set. It is well known that the numerical radius forms the norm of the C-star algebra of bounded linear operators, and this numerical norm is equivalent to the standard operator norm through a relationship given by this inequality. This inequality holds with equality under specific conditions, such as a squared equals 0 for the lower bound and a being a normal operator for the upper bound. Now we will introduce the topic further. In addition to the investigation of inequalities of numerical radius, recently the authors introduced the generalized real and imaginary part of an operator given by these quantities, where v is a parameter from 0 to 1. When v equals 1/2, they reduce to the well-known real and imaginary parts. Utilizing these generalized real and imaginary parts, the authors defined the v-weighted numerical radius as follows. In their work, they also explored several properties of this weighted numerical radius, deriving various inequalities, including this inequality. In this work, we will generalize their concept, prove that our generalization is indeed a norm on C-star algebra of all bounded linear operators, and that is equivalent to the operator norm. We will also obtain various inequalities that generalize the existing ones. To achieve our results, we will need some lemmas. So the following result was given by Dragomir in his paper. This is a famous result for the numerical radius of the product of operators for the power of r greater or equal than 1. And the next result concerns us with the non-negative convex functions and can be found in this paper. So the direct sum of two copies of Hilbert spaces is denoted by H, direct sum H. If A, B, C, D are bounded linear operators, then the operator matrix can be seen as an operator acting on H, direct sum H, and is defined as this. And the following lemma we also need is well known. It concerns itself with the 2x2 matrix, the norm of the said matrix. It is just the maximum of the diagonals. We define the following class of functions, which will be used throughout the paper. We say that H and G belong to the class of Q if they map from some subset of R to R. We utilize the following generalized definitions of the real and imaginary parts given by Kitanek and myself in another paper we submitted. Let A be a bounded linear operator and let H and G belong to the previously defined set. We define the generalized H, G, real and imaginary parts of an operator like this. Now setting G of t equals to H of 1 minus t and K to be 0, 1, and letting H be identity, we recover the generalized real and imaginary parts of an operator defined by the previous authors. And if we also set F and G to be 1/2, we recover the regional definitions of the real and imaginary parts of an operator. Now we proceed to the main results. We define the generalized numerical radius of A as follows. It is defined like this, as this quantity, where H and G, it should be H, not F here. It is H and G belong to Q, and the generalized numerical radius is defined like this. Now the theorem states that this is indeed a norm. For that, we need A to be a bounded linear operator. H and G belong to Q. They are not zero, and H is different than minus G. And then this function is a norm. The non-negativity follows from the fact that this is non-negative by definition. And now let us assume that A is zero. Then clearly this is also zero by definition. It is trivial. Now when we assume that the left-hand side is zero, then we have that this equation holds for all phi belong to R. Setting phi equals zero, we get this. And then when we set phi equals pi over 2, we get this. And when we add those two equations, we get this. And here we utilize the fact that H is not equal to minus G and they are not zero. And then we can divide both sides to get A equals 0, and then also A adjoint equals 0. Now we need the homogeneity. Let alpha belong to the field of complex numbers. Then we have this quantity. And now we utilize the fact that for every non-zero complex number alpha, there exists beta from R, such that alpha is the module and the angle of the said number. And utilizing this fact, we just this is just simple algebra. We recover this quantity. Now we introduce the substitution of phi plus beta equals beta prime, and then we recover this identity. And since phi ranges over all real numbers and beta is a fixed number, then beta prime also ranges over all real numbers. Therefore, this quantity, beta prime minus beta, can be replaced with just beta prime, as the sets of the supremum remain the same. So this simplifies to this, and this is just the same, rename beta prime to phi, and that's it. And the triangle inequality is trivial, just separate the terms, and we will get the said inequality. Therefore, we have proven that this is indeed a norm. Now, as previously stated, setting H equals identity, G of t equals 1 minus t, K to be 0, 1, we recovered the numerical radius definition given by the authors previously stated. We recovered exactly this. Now, let A be a bounded linear operator and let H and G belong to Q. Then this inequality holds. Now let us consider this quantity square. We use the fact that this is nothing but norm of A adjoint A, and then we multiply it out, and this is just the triangle inequality for the norms. This quantity, first one, is self-adjoint, therefore its norm is given by the supremum of the module, and then we will separate it with the triangle inequality for both terms. The second term, we just leave it as it is. And when we separate, when we separate the terms, the second one is left as it is. We get to the original inequality. Setting H to be an identity, J of t equals 1 minus t, K is 1, 0. We recover the inequality given by the previous authors. And also when we set H and G to be 1/2, we recover the inequality given by Abu Omar and Kitaneh in their work. And from this inequality, we can also see, we can recover the inequality given by El Haddad and Kitaneh in their paper. That is their case when L equals 1. So this is the corollary. Starting from the previously obtained inequality, we use the Dragomir's inequality for the product of two operators to get this, and just add those two terms to get the inequality given by Kitaneh. The following theorem is as follows. Let A be a bounded linear operator, H and G are belonging to Q, be non-negative, and M of A is the infimum of this quantity. Then the following inequality holds, this double inequality. To start, let X be an arbitrary unit vector and let phi belong to R be such that this identity holds. Using this, we have the following. Just to square we square the quantity, and we use the same trick as previously, just A adjoint and A, where A is equal to this. And since this is self-adjoint, its norm is the supremum of the module, and this is greater or equal than just the module, as usual. When we multiply out the terms, we get this, and real part comes out, and then we use this fact from the beginning. So this term simplifies to this, and this is greater or equal, this term is greater or equal than the infimum of this term. And then we take the supremum of all the unit vectors, and we obtain the desired inequality for the left-hand side. To get the right-hand side, we use the same trick, but this time it is way easier since we can just separate the two terms. This term is nothing but the numerical radius we just defined. This is a typo. This shouldn't be numerical radius of a squared, but the numerical radius of the term we just used. Now the following theorem is the usual one when one defines generalized numerical radius. Let A be a bounded linear operator and H and G belong to Q. Then for alpha beta belonging to R, we have this identity. This identity is easily proven. We just consider the generalized numerical radius given by the formula from the beginning, and we write out this term, and we just smartly group the terms from which we get this. Now we let alpha equals cosine of beta and beta equals sine of alpha, and we observe that since cosine and sine satisfy this and alpha beta satisfy it, the sets are the same, and so we obtain the desired expression. Setting alpha beta to be 1, 0 and 0, 1 respectively, we obtain this inequality. This is the usual thing that holds for the numerical radius. Now we have the corollary, and we start by utilizing the representation of the generalized numerical radius, the one we just obtained. We use here the triangle inequality, and then we use Cauchy-Schwarz inequality, and since the supremum is 1, it reduces to the inequality as desired. Now we have the equivalence of the norms. Let A be a bounded linear operator, and let H and G belong to Q be of the same sign. Then this double-sided inequality holds. Now consider the inequalities we just obtained, the ones that the generalized numerical radius is greater or equal than the real part, generalized real, and generalized imaginary part. We add those two things, and this is greater or equal than this. And this, when simplified, results to this. And when we use the reversed triangular norm inequality, which simplifies to this. And here we use the fact that H and G are of the same sign, so this constant is greater than 0. For the upper bound, we use the original definition of the numerical radius, and we just split the terms, and this is far easier to see that this is greater or equal than 0. Combining the left and right-hand side inequality, we reach the desired conclusion. Now we move to the matrix type inequalities. Suppose that T equals this 2 by 2 matrix, A, B, 0, 0, where A and B are bounded linear operators, and let M be the maximum of these two functions. Then this inequality holds. Now let phi be arbitrary. Now consider the following. This is just written out. When you apply the definition, you will obtain this expression. When we square it, we have this expression. Now taking the norms and utilizing 3, 3. It is the lemma at the beginning that the norm of the 2 by 2 matrix of the diagonal is the maximum of the norms. So we apply it here. The first term is nothing but the norm of this term, and B star, B, that is the same. So it reduces to a norm of B and then squared. And this is just the maximum of these two terms. Now we bound this term by the definition. This is just the norm of the real part, but this is just a supremum. So it's less or equal than. And here we use the submultiplicativity of the norm. We bound this part and this part independently. And then we use the M as a maximum of these two functions to bound this part. And then this part, the norm of this, is nothing but is less than equal than the generalized numerical radius. Now we take the supremum over all angles, and we obtain the desired inequality. Now, setting h and g to be 1/2, we recover the inequality given by Bunia and others. And in this paper, which is the theorem 9, that is this inequality. Now we have the following corollary: let A, B, C, and D be bounded linear operators, and let H and G belong to Q. Then this inequality holds. We first start by observing that this is a unitary operator, utilizing the subadditivity of the numerical radius together with weak unitary invariance property, that is this one. For the unitary U, we obtain this. So this first inequality is nothing but the subadditivity of the numerical radius. And the generalized numerical radius also satisfies the weak unitary invariance. This should be generalized numerical radius, not the numerical radius. But it also satisfies the same weak unitary invariance property. So when we apply it here, this matrix shifts the two operators down to upper part, and then we use the inequality previously obtained for the upper operator matrix on both the terms. Now let A be a bounded linear operator and let H and G be linear functions belonging to Q. Then this is a convex function on 0, 1, and we also have this inequality. To see that F is convex, one can easily check by definition. This is trivial to check when this is just the simple definition of the convex functions. It shouldn't be hard. And for the proof of this inequality, you will utilize the famous Hermite-Hadamard inequality. That is this one where F maps from A, B to R, and this is convex. To obtain the desired inequality, we set A equals 0, B equals 1, and apply the said inequality to the convex function already stated. And me and Professor Kitanek also obtained several other inequalities, but I didn't want to include everything from the paper since the talk is only 20 minutes. So I will also mention this is the inequality mentioned by Professor Paul from the first lecture yesterday, that the numerical radius satisfies something like this. And this also satisfies, and it is also satisfied by the generalized numerical radius. It is the same inequality. The proof is very similar. And this is also, and the corollary of this one is also that if generalized numerical radius is it equals to this or this, then the real and imaginary parts are equal to this or this. It is easily shown by using this inequality. And the proof is somewhat similar to the original proof by using the normal numerical radius. So this study successfully develops a novel and adaptable framework for numerical radius inequalities by introducing the generalized numerical radius derived from the generalized real and imaginary parts of an operator. We have established that this numerical radius functions as a norm and demonstrated its equivalence to the standard operator norm. A key strength of this framework lies in its generality, as it not only recovers numerous existing numerical radius inequalities as special cases, such as those presented by the author and others and Kitanek, but also provides new identities and sharper bounds. The inherent flexibility offered by the functions H and G suggests promising paths for future research, particularly in the analysis of dynamical systems in which operator properties may evolve. So this is it for the talk. I spoke with some people that conduct research in physics, and they told me that this definition of numerical radius can be used to greatly improve some stability issues that can arise in dynamical systems. Since this numerical radius encompasses in its definition the weighted term H and G, which can be chosen according to the physical behavior of the dynamical system. So this numerical radius, apart from the inequality standpoint and the theoretical mathematics point, it can also be used to improve various things in physics, as I have spoken with many of my colleagues. So the references are here, and that's it for the talk. If you have any questions, feel free to ask.